Look at your hand right now. You can see it because light is bouncing off it and entering your eyes. This seems straightforward. Light travels in straight lines from a source, bounces off objects, and reaches your eye. That's how you see. But here's a question. If light always travels in straight lines, why can you see around corners? Why can you hear someone calling from another room even though you can't see them? Light does something that seems impossible at first. And this confused the greatest minds in science for centuries. Today, we're going to explore why light behaves in ways that feel confusing, not because physics is mysterious or contradictory, but because our everyday intuition about how things should move is incomplete. Let's start with what you think you know about light. When you turn on a flashlight, the light travels in a beam. It goes in one direction. It doesn't spread out too much. If you shine it at a wall, it makes a bright spot. This matches your intuition perfectly. Light is like a projectile. It shoots from a source and hits a target. You might think of light like tiny particles flying through space. Imagine throwing a ball. It leaves your hand, travels through the air in a path you can predict, and hits something. Light seems to work the same way. This intuition is so strong because it matches what you see every day. When you look at a spotlight cutting through fog, it looks like a beam of particles. When you see a ray of sunlight streaming through a window, it looks like a straight path. And here's the thing. This intuition isn't wrong for everyday purposes. Photographers use it. Artists use it. Architects use it. For most practical purposes, thinking of light as traveling in straight lines works perfectly. But there's a catch. Light sometimes doesn't behave like a projectile at all. And that's where things get confusing. For most of history, people didn't really understand what light was. They just observed its behavior. They noticed it travels in straight lines. They noticed it reflects off mirrors. They noticed it bends when it enters water, which is why a stick in water looks broken. In the 1600s and 1700s, scientists had two competing ideas. Some thought light was made of particles, tiny bullets shot from a source. Others thought light was a wave, like ripples spreading across a pond. Both ideas had evidence supporting them. Particles could explain why light travels in straight lines and why it reflects sharply off mirrors. Waves could explain why light seems to spread out sometimes and bend around obstacles. For a long time, the particle idea was favored. Isaac Newton was a huge supporter, and his influence meant particle theory dominated for a century. But then, in the early 1800s, an English scientist named Thomas Young did an experiment. He shined light through two narrow slits and looked at what appeared on a screen beyond them. If light were particles, he should see two bright spots directly behind the slits. Instead, he saw a pattern of light and dark stripes, an interference pattern. The kind of pattern you see when water waves pass through two openings and interfere with each other. This was shocking. Light seemed to behave like a wave after all. The wave explanation became dominant. And it worked wonderfully. Maxwell's equations, published in the 1860s, described light as a wave, specifically as a wave of electromagnetic energy. This explained reflection, refraction, and diffraction. It explained colors, rainbows, and shadows. The wave model was so successful that the particle idea seemed dead. Except it wasn't. Here's where things start to get confusing. In the early 1900s, scientists began noticing something strange. When light shines on a metal surface, it can knock electrons off that surface. This is called the photoelectric effect. But here's the weird part. The energy of those electrons depends on the color of the light, not on how bright the light is. If you use dim blue light, the electrons fly off with a lot of energy. If you use bright red light, the electrons barely move at all. This doesn't make sense if light is a wave. A brighter light should deliver more energy, regardless of color. But it doesn't. The color, the frequency of the wave, is what matters. Albert Einstein explained this in 1905 by suggesting that light comes in packets, or quanta. Each packet has an energy that depends on its color. Blue light packets have more energy than red light packets. This is why blue light knocks off faster electrons. But wait, this means light is made of particles again. So which is it? Is light a wave or a particle? Here's where you hit the limit of your intuition. The answer is, It's both. And neither. It's something else entirely, something that behaves like a particle in some situations and like a wave in others. When light passes through two slits, it behaves like a wave. It spreads out and creates interference patterns. When light hits a metal surface, it behaves like particles. Individual packets of light each knock off a single electron. The same light. Different behaviors. Depending on how you look at it. Now, this might sound like a contradiction. How can something be a wave and a particle at the same time? How can it behave differently depending on how you observe it? This is where physics becomes genuinely interesting and where your intuition really starts to fail. The issue is that wave and particle are categories that come from everyday experience. You know what waves are. You've seen ripples in a pond. You know what particles are. You've seen dust floating through air. But light isn't actually either of these things. Light is something more fundamental. It's part of nature that doesn't fit neatly into either category. In quantum mechanics, the modern physics that describes light at its most basic level, light is described as a quantum field. It's a field that exists everywhere in space, and it has a specific way of interacting with matter. When you measure light a certain way, by looking at whether it passes through two slits, you set up conditions where light behaves like a wave. It interferes with itself. When you measure light a different way, by counting individual photons hitting a detector, you set up conditions where light behaves like particles. You count individual packets. This isn't a contradiction in light. It's a limit of the everyday categories we use to describe things. Think about it this way. You've never encountered anything in your everyday life that behaves differently depending on how you measure it. A ball is a ball whether you weigh it or measure its size. But quantum objects, and light is one of them, have a fundamental property. How you measure them affects how they appear. This isn't because measurement disturbs them in a simple way. It's because at that level of reality, what it really is, independent of measurement, isn't even a meaningful question. So let's talk about what physicists actually mean when they talk about light, and what they do not mean. When a physicist says, light is a wave, they mean, in these particular experimental conditions, light behaves according to wave equations. It shows interference and diffraction. It has frequency and wavelength. When a physicist says, light is a particle, they mean, in these other experimental conditions, light behaves as discrete packets, each carrying a definite amount of energy. What they do not mean, light is secretly one of these things, and we're just pretending it's the other depending on convenience. What they do not mean, light is actually paradoxical or illogical. What they do not mean, science doesn't understand light. Science understands light extremely well. So well that we've built lasers, fiber optics, digital cameras, and countless other technologies based on this understanding. The confusion comes from trying to force light into categories it doesn't fit. It's not that light is mysterious. It's that light is more fundamental than the everyday categories you intuitively understand. Here's an important point. This isn't unique to light. Every quantum object, electrons, atoms, photons, behaves this way. It's not a special weirdness of light. It's a feature of reality at small scales. Let me give you another example to show why your intuition breaks down. Imagine you're at a concert. You're in a room where you can't see the stage, but you can hear the music. The sound waves are spreading out in all directions, including around obstacles and through doorways. That's why you can hear even though you can't see. Light, by contrast, travels in straight lines. You can't hear something if there's a solid wall between you and the source, but you can't see it either if a wall is in the way. Light doesn't bend as easily as sound, but it does bend. If light passes through a very narrow opening or near the edge of an obstacle, it spreads out. This is diffraction. Light bends around obstacles. Now, if you make the opening narrower and narrower, the diffraction becomes more pronounced. The light spreads out more. But here's the strange part. This is exactly what waves do. The narrower the opening compared to the wavelength, the more the wave spreads out. Light is showing wave behavior. But if you make the opening even narrower, smaller than the wavelength of visible light, something interesting happens. You can't actually observe the light passing through anymore. The light itself changes. The smallest opening that can meaningfully interact with light is on the order of its wavelength. And at that scale, quantum effects become important. You can't separate the light from the apparatus observing it. This is why intuition fails. You're used to watching baseballs or water droplets pass through openings. These are large compared to their wavelengths, so they always behave as particles. Light, at its fundamental scale, is not large compared to its wavelength. So it doesn't behave like a particle at all. Here's what's really happening. Light is a phenomenon that exists at scales where your intuition doesn't apply. Your intuition comes from observing objects that are millimeters, centimeters, meters in size. Your brain evolved to navigate a world at the human scale. Intuition is great for that world. But light's fundamental properties show up at scales billions of times smaller. Wavelengths of visible light are around 500 nanometers. That's 500 billionths of a meter. At that scale, the rules of quantum mechanics apply, and they're very different from the rules you intuitively expect. So light doesn't behave in confusing ways. Light behaves exactly the way quantum mechanics predicts. Your intuition is just based on a different regime of physics. This is actually a profound insight. The world you experience directly, the everyday world, is governed by rules that are much simpler and more intuitive than the fundamental rules. At everyday scales, quantum weirdness averages out. Things appear classical. Particles behave like particles. Waves behave like waves. But zoom into the scale where light lives, and the fundamental nature of reality becomes visible. And yes, it's strange compared to everyday experience. But it's not illogical. It's just different from what you're used to. So why does this matter? Why should you care about how light behaves? Because understanding light is understanding how the universe works at its most basic level. Light is part of the electromagnetic force, one of the four fundamental forces of nature. Understanding light means understanding how atoms emit and absorb energy. It means understanding chemistry. It means understanding why matter is stable. And practically every technology that uses light, and that's basically all modern technology, is built on the quantum understanding of light. Lasers, LED lights, solar panels, fiber optics, semiconductors, all of these depend on understanding that light behaves like both a wave and a particle depending on how you interact with it. Let's come back to where we started. You see your hand because light is bouncing off it. That's true. Light does travel in generally straight lines, and that's a good way to think about it for everyday purposes. But light is more than that. It's a quantum phenomenon. It's part of the fabric of reality. It doesn't have to choose between being a wave or a particle because those categories don't actually apply at its fundamental level. Does this mean your everyday intuition is wrong? It means your intuition is limited. It applies to the human scale world and it works great there. But reality extends beyond that world. And when you look at light closely, you're seeing into a realm where the rules are different. This is how science actually works. It doesn't contradict everyday experience. It builds on it. It explains why everyday experience is the way it is. And it reveals deeper layers of reality that everyday intuition can't reach. The confusion you feel when thinking about light isn't a sign that physics is broken or that you don't understand. It's a sign that you're encountering something genuinely fundamental about how the universe works. Light isn't strange. Your intuition is just calibrated for a different scale. And that's beautiful, actually. It means reality is far richer and more layered than what you can directly observe. It means there's always more to understand. The next time you see light, remember that you're looking at something that behaves in ways that confused the greatest minds in history. Not because they were missing something obvious, but because what's obvious at the human scale becomes subtle and unexpected at the scale where light lives. And understanding that difference is the beginning of understanding physics.